All right, here we are again. So let's see. So for today, we have a few things to do. We do have some problem sets to work on. And let's see, there should be two of them. There's more, but we'll start with the first two, just again to make sure that we're all caught up. And then I've got some cool videos for you to see that I think I said that we would watch, but hold on one second. Let me go to Moodle and see if I posted them. Yeah, if they're not there, I'll put them there because I want you to be able to check them out afterwards. If you want to watch the videos again, it would be nice if you have the links. So I'm trying to make sure that all the links are on here, along with the notes, of course. No, they never got there, did they? All right. I'll tell you, I'll take care of that later. I've got the links right here in a Word document anyway. So, but before we start, let's take a look at these problem sets. Number one, for example, is right here, and I hope you had a chance to look at them, and then we'll follow that up with number two. Number three, I decided to save that for next week because we haven't quite finished that material yet. It's right here. Let's take a look at it for a second. Yeah, this one is all from the section that we're about to look at. As far as the notes are concerned, we have chapter one broken up into two parts, A and B. So A is pretty much done. All right. In fact, let me go get it back so we can remind ourselves what we were just doing last week. Let's see, where is it? A. There it is. Yes, so we've covered a lot of ground, but there's a lot more to go. So we looked at all these cool functions. And let's see, I'm pretty sure we finished this section. Yeah, because, oh, that's right, composite functions. That's right. That was the last thing we were doing. Okay. And so this week, we'll pick up with 1B. In the beginning, there's a lot of focus on graphs. And so we may lean on our friend Symbolab to help us with this. But then after that, it moves into other territory, more discussion about functions and a lot of good stuff. And then if we do somehow finish that, chapter two is waiting for us here. This one's a little shorter. This is just exclusively about linear functions, a specific type of function that we're all very familiar with. In other words, I'm sure you'll recognize the equation of a straight line. So all the functions that have this form are referred to as linear functions. And in fact, we use these quite a bit in practice. A lot of applications are based on linear functions. So this is an important topic. That is right here. Okay, so that's been posted. So the only thing I didn't get posted was the links to our videos, which is fine. I'll do that later on. So first, let's take a look at the practice problems and make sure that we're all following along and we're not falling behind. And then we can get to the videos and then we can dive back into the new material. It should be a good day. All right, a lot of cool math for us as usual. So, all right, let's take a look at these. Let me just quickly do one thing. What is today? The 17th. Okay, it's hard to believe we're already more than halfway through February. This year we have only 28 days, of course, as usual, except for presidential years. And yeah, March is just around the corner, isn't it? Well, not really, but I mean, what is it, like a week from Monday? Man. So once the semester actually got started, things have been flying, haven't they? Now, as far as I know, there are no more days off. We're just going to go right through to May, but that's, because we had a long Christmas break. All right, so let's take a look at some of these. So first of all, when it says to evaluate, the word evaluate means basically plug in a number. So here, for example, the first one is f of -3. What that means is literally wherever you see an x, replace it with -3. All right, so that's all you have to do. And the purpose of doing this is to come up with a specific value rather than a function. So here, for example, you would just say, all right, well, f of negative 3 would be 2 times negative 3 minus 5, which is minus 6 minus 5 equals minus 11. And it's just that simple. F of 2 would then be 2 times 2 minus 5, which is 4 minus 5, which is negative 1. Now, this is where it gets a little strange. F of negative a is clearly not a number, but we can still do this by just replacing all the x's with negative a's, and this would be our final result. We can't do anything else with it unless we know the identity of a. How about negative f of a? Now, this is a little trickier. Well, not really, because what you're doing then is you are taking f of a and multiplying it by negative 1. So we're going to start by calculating f of a. I'll just write the negative on the outside to remind us that what you're actually doing is you're evaluating this function at a, and only then do you apply the negative. Okay, so you've got negative 2a minus 5. So when you're finally done, you have minus 2a plus 5. So that's why we have to be very careful with this thing, because the negative comes last. So what you should ideally do is evaluate f of a and only then apply the negative. Now, and then we have one more, f of a plus h. All right, it's a little bit more involved. Well, it's not that bad this time. So now here with the 2 times a plus h, you can use the distributive property to rewrite that as 2a plus 2h minus 5, and then you're done. You can't really do anything else with this one. All right, now let's do this. Now this next one is going to be a little bit challenging because we've got squares involved. Okay, so hold on one second. Let me split the screen up so I don't have to scroll back and forth. All right, there we go. So for number 2, we're going to evaluate the same 5 cases. So we'll start with f of negative 3. So we'll have minus 5 times negative 3 squared plus 2 times negative 3 minus 1. So we'll have negative 5 times 9 minus 6 minus 1 minus 45 minus 6 minus 1 is minus 52. Okay, and then f of 2 would be minus 5 times 2 squared plus 2 times 2 minus 1 equals minus 5 times 4 plus 4 minus 1 minus 20 plus 4 minus 1 is minus 17. All right, how about f? Now this is where it gets really tricky. Well, I don't know. This one isn't that bad. Some of the others might be worse. 5 times minus a squared plus 2 times minus a minus 1. So we have minus 5 times, now negative a squared is just a squared. Oops. Now the next one, 2 negative a, this one becomes negative 2a minus 1. And here we're just done. You can't take it any further than that. Negative f of a, again, keep the negative on the outside. And then evaluate this at a, okay, negative 5a squared plus 2 times a minus 1. So keep the negative on the outside. So this one is minus 5a squared plus 2a minus 1. And now when you apply the negative to all those terms, you'll end up with positive 5a squared minus 2a, minus 2a plus 1. So you're basically just reversing all the signs. And then now this one, Wow, this is going to be a bit of a challenge. All right, but let's try it. So a plus h is squared now. Then we'll have 2a plus h. So we're going to have a lot of multiplying to do here. Now, just as a side note, a plus h squared, what do we do with that? There's a couple of techniques that we can use. Why don't we rewrite this as a plus h? A plus h. Now, you might remember this technique you learned in high school called FOIL. When you have a binary expression like this that's multiplied by another binary expression, you can use the FOIL technique, where, of course, these letters stand for first, outer, inner, and last, right? Let's see. Let's make some space here. All right, so F means basically these two are multiplied together. This is F. That gives me a squared. O would be these outer terms, AH. I is the inner, this is O. I is these two inner terms. Again, that's AH. And then you've got H, last is H times H, which is H squared. So when you consolidate these terms, you've got A squared plus AH plus AH plus H squared, which would be simplified into A squared plus 2AH plus H squared. And that's what's, let's come back up here. Now, the reason why I went through all these steps is because that's what's going to take the place of this expression. Okay, so that means that this is now equal to minus 5 times, inside the parentheses, we have all of this. Okay, and then now for this one, we can just multiply the 2 by all the terms inside. And then now the last step is to multiply the negative 5 by these terms. So we have negative 5a squared plus 10ah plus 5h squared plus 2a plus 2h minus 1. So now what we should do is consolidate all the like terms, if there are any, which actually I don't think there are any. We're actually done here. We can't combine any of these terms any further. So that means that we're just done. It's a little surprising, but yeah, that's it. Oh, I just realized you're right. I hope that's what you're telling me. I missed one of them. Yes, you're absolutely right. I blew it. I missed the two negatives, actually. Thank you. See, when you multiply this negative 5 by what's inside, you need the negative and the 5. So I did blow it here. This should be minus 5a squared minus 10ah minus 5h squared. These are fine. Okay. So now it's correct. Very good. All right. And again, since you can't consolidate any of the terms, since they're not even numbers, then you can leave it like this. If you had numbers, then you could consolidate this into a single value. All right, beautiful. All right, so that was not as bad as maybe it looked. All right, now let's get to the next one. Let's see. Oh my God, square roots. Ooh, this is going to be tough. Yeah. All right, oops. Yeah, I'll do this one by hand. So we'll start with f of negative 3. I could type this in the equation editor, but this will just be faster. So just remember that all the x's are being replaced with a negative 3. And so here, this is 2 minus a minus 3. This is radical 5 plus 5. And that's the end of that one. F of 2 would therefore be 2 minus 2 plus 5. And of course, radical 0 is just 0, any way you look at it. F of negative a would be 2 minus a minus a plus 5. So we end up with radical 2 plus a plus 5 on the outside. Then we need negative f of a. Okay, so since the function is 2 minus x, it becomes radical 2 minus a plus 5. Oops, wait. Let's try that again. We'll put the negative on the outside. Then in parentheses, I'll evaluate this at a. That's radical 2 minus a plus 5. All right, it insists on showing us the weather. Plus 5. Nope, sorry. Now I can close the parentheses. In other words, this is all f of a because the original function is radical 2 minus x plus 5. So the x is replaced with an a. The negative stays out here. Now I have to multiply it through, and I'm going to get minus radical 2 minus a minus 5. Okay, and then finally we have f of a plus h. And remember, the original function was 2 minus x. So here we've got to replace x with a plus h in parentheses plus 5. And so here all I have to be careful about is to make sure the negative is applied to each term in these parentheses, 2 minus a minus h plus 5. And then I can't simplify this any further. So that one's done. All right. Oh, there's so many more. All right. Just want to make sure everyone's caught up. Okay, so they're all together now. Okay. Now how about 4? Oh, there's just this one. All right. So we have to go through the same routine, but for these 4 values. Now this is a ratio. And in most of these cases, there'll be very little simplification that we can actually do. Very little. But that's okay. It's not always possible to simplify our expressions. All right, here's f of negative 3. So what I'm going to do is replace all of these x's with negative 3's. And so I'll end up with a number of some kind. The numerator, I have negative 18 minus 1. And in the denominator, I have minus 15 plus 2. And the negatives do cancel out. And so I end up with 19 over 13. And that's that. Next is f of 2. Try that one. All right. A 2. We'll have a 2. And a 2. And that's going to be 12 minus 1 over 10 plus 2 equals 11 over 12. And that's it. We're done. Okay, beautiful. Now C. Now we're doing the abstract ones. F of negative A. Okay, let's see. Minus 6A minus 1 plus 2, and we're done. D. This is the negative f of A. Okay, the one we have to watch out for. So we'll put the negative here, and then each of these x's becomes an A. Now this one is done. There isn't anything we can do with it. All right, and then the next one, the last one, f of A plus h. By the way, I'm going to post these solutions on Moodle when we're done. So if you miss something, that's okay. You'll have a copy of this. So yeah, we can just replace this with A plus H. And then we can extend it, expand it a little. And 6A plus 6H minus 1, or 5A plus 5H plus 2. And that's it. There's no simplification there. Okay, so that block is done. Now, what's nice about this next group is that they're all numbers. Okay, every one of these is just all numbers. And so no matter what happens, we won't get any messy algebraic expressions. And that's what I like. Okay, numbers, we like numbers. So 4 minus 2 times negative 2, 4 plus 4 equals 8. F of negative 1 is 4 minus 2 negative 1 equals 4 plus 2. I'm going to be careful with those negatives. F of 0 is the easiest one, because you just end up with 4. F of 1 is 4 minus 2 times 1, which is 2. And then finally E, F of 2 is 4 minus 2 times 2, which is just 0. Wow, that was easy. I like that. All right, so let's see. Let's split up the screen and apply these to the next one. F of negative 2 equals 8 minus 3 times negative 2, which is 8, plus 6, which is 14. Is that right? Yes, it is. Okay, hold on one second. I have to make a change here somewhere. Oh, I'm looking at the wrong one. Oh, no, we got it. No, that's not right. Hold on a second. Okay, so then we have f of -1, 8 minus 3 times -1 equals 8 plus 3, which is 11. F of 0 equals 8 minus 3 times 0, which is 8. F of 1 equals 8 minus 3 times 1, which is 5. F of 2 is 8 minus 3 times 2, which is 2. All right, very good. Now, number 7. This one's a little trickier because we've got squares involved. That's all right. We can do this. Oh, you know what I forgot to do? I forgot the letters. We want to label everything. All right, let me make sure I did that. Yeah, I did it up there too. All right, very good. All right, so let's do it again. F of -2 equals 8 times -2 squared minus 7 times -2 plus 3, which is 8 times 4 plus 14 plus 3 is 32 plus 14 plus 3. That should be 49. Yes. Let me just double check that. 8 times 4 minus 7 times -2. That's 32 plus 14. Yep, that's it. All right, let's try the next one. How about -1? All right, so we're going to have 8 times 1. -1 squared, of course, is 1, plus 7, plus 3 equals 18. Okay, f of 0. Now this will be easy because 2 of the terms will just drop out. I like that. F of 1 is 8 times 1 squared minus 7 times 1 plus 3, which is 8 minus 7 plus 3, which is 4. Okay, and then finally E, f of 2 would be 8 times 2 squared minus 7 times 2 plus 3 equals 8 times 4 minus 14 plus 3 equals 32 minus 14 plus 3, which is 21. All right. All right, now the last one involves a radical, which is a little scary. So let's see. I'll do this one by hand. So we start out with three plus under the square root sign, -2 plus 3. Oops. Okay. Oh, what did I do? This is equal, sorry. All right, so it's 3 plus -2 plus 3, or 3 plus radical 1, 3 plus 1, which is 4. B, so this time we're replacing it with -1, 3 plus radical -1 plus 3. And this time we can't do anything with it. It's just 3 plus radical 2. F of 0 would be 3 plus radical 0 plus 3. 3 plus radical 3. And again, we're finished. There's nothing else we can do with this one. It's as simple as it's going to get. D, f of 1, is 3 plus radical, oh, here we go. This one we can do something with. Because, of course, radical 4 is just 2. That's 5. Okay, and then finally we have E, f of 2 is 3 plus radical 2 plus 3. This one we can't simplify anymore. It's just 3 plus radical 5. All right, well, that was a lot of good practice evaluating functions, I must say. So I hope you got them all right. If not, I mean, just remember too, I mean, if you have a mistake, it's almost certainly an algebraic error. You're literally, again, like I said, you're just literally substituting whatever the value they give you for all the x's in your function, and then just calculating the final answer. So there's nothing conceptually difficult about this, but you will probably find that it's easy to make mistakes just because, you know, there's negatives and there's square roots and all the rest. So for these, it's just a question of being careful. In fact, I wasn't always careful either. So you just, you know, keep an eye on all those steps and you should have the right answers. So yes, I'll post this when we're done. And so now let's take a look at number 2, which I think might be a little easier. Oh no, these are different. These are conceptual questions, a little bit, well, kind of conceptual. We're looking for domains in these cases. And so just basically remember that the domain is essentially just all the values of x that can be substituted into this function. All right, that's really all that it is. In other words, what you're looking for is values of x that cannot be substituted into this equation. Now, this one is a little challenging because if you look at it carefully, x squared minus x minus 6, you can rewrite this by factoring it. So you might recall how that works. You're trying to find two expressions, two binary expressions, where their product equals this result. Now, if you've forgotten how to do this, just think about it this way. Let's take a step back here. If you were to multiply out x plus m times x plus n, these could be any two real numbers. Based on FOIL, let's do a little foiling on this. This would be your first. X squared. Outer is here. Inner would be these two. M times x. And last would be these two. NM. Or actually, let's do it in alphabetical order, not that it really matters. MN. And we'll consolidate these to come up with x squared plus n plus mx plus mn. So up here, you should be able to tell by looking at this one, n plus m equals the coefficient of x, which is -1. and m times n. What did I do here? Oh, I wanted to do these. Like I said, it doesn't make any difference. I just would rather have them in order. M plus n. I don't know if that's, yeah, I don't remember the proper name for this technique. If you remember hearing it called that, that's fine. I'm sure that that's correct. Yeah, because what I'm basically doing is showing you algebraically. What does AM stand for?
I don't know what it's called per se, but it's the middle term of the polynomial, and then the last term is n. So basically, you would try to, make an X diagram to find what two numbers add to the middle term, but also multiply to your last term.
Right. Yeah, there's so many different ways of doing this. The way I like to look at it is this. So we start out by noting that we multiply these two terms together with FOIL. This is the final result. So based on this expression up here, this m plus n is -1 because that's the coefficient of x. This last term, this constant, is mn. Now, what we have to do now is look at this -6, and we need to find all the pairs of integers whose product is -6. Now, this is not the only way of doing this. So for example, you could try 1 and -6. You could try that, right? You could try -1 and +6, 2, -3, -2, 3. And I think that covers all the possibilities. But in only one of these cases, the one that we're looking for is the sum equal to -1. So in other words, we need to make sure that the numbers we choose, m and n, are such that their product is -6 and their sum is -1, and that only happens here. So that means it must be the case that this expression is the same as x plus 2 times x minus 3. And we can prove it with FOIL. X plus 2, let me split the screen for a second. So you can follow along and see what I'm doing. So we're going to try to prove that what we've just done is correct. X plus 2 times x minus 3, let's confirm that it equals this expression up here. And again, let's try with FOIL. Because I don't know, it just seems like the way to go. Although there are other things you could do here too, which I'll show you one that I know, which you might like even a little better. But we'll start with FOIL. And finally, L, whoops, losing my place. There we go. F is these two. O is these, the outer two. Minus 3x. Inner would be these two. And then last would be these two. So this gives us x squared minus x. Oh yeah, what do you know? It works. So the point of all of this is that I can rewrite this expression that I started out with. And we're doing this not just for the fun, but I almost forgot to show you my other technique. X plus 2 and x minus 3. This is something that you might have seen. If you line them up like this, x plus 2 and x minus 3, what you can do is essentially just multiply each term by all the other terms. In other words, we start here, then we go across here, then we go across here, and then we go up to x squared. And the advantage of this approach is that we're not just restricted to quadratic equation formulas. This can apply to polynomials of any size. So that's another technique you could try if you want to multiply these terms together. But anyway, the purpose of all this was to say, listen, look what happens here. I can rewrite this as, all right, equals. And then we take these two factors that we just created, x plus 2, and x minus 3. Okay. Why does that matter? Because now it's clear that we cannot allow x to be -2 or +3, because that would lead to division by 0. And that's exactly what we have to avoid. So therefore, the domain can be written in this interval notation as everything from -infinity up to, but not including -2. Then we combine that with a union symbol. We can allow anything between -2 and 3, but not including -2 and 3. Therefore, we have the round or the parentheses. And then 3 itself can go, we can now go from 3 to infinity, again, leaving out the 3. So in other words, the fact that these are round, this means not including -2, and also not the round bracket over here means not including 3. Same thing here and here. So in other words, this is just a fancy way of saying all real numbers except -2 and 3. That's just a very fancy way of saying this. In fact, in some books, what they'll say is all you have to do is write this. X is not equal to -2, that kind of thing. But this is the more formal way of writing it, the interval approach. Now, let's go visit. Now, I think I introduced this to 1 week, Symbolab. It's a very good tool for graphing these types of insanely complicated functions. So let's see. We're going to have 1 over x plus 2 and x -3. Now, it's a little, let's see if we can get in a little closer. Yeah. You know what? Let me do this. I think it does a better job on this page. Oh, yeah. You have to know how, I mean, it's a little quirky, this thing. So first you have to write it as an equation rather than just this expression, and then it'll, oh, it's not offering to graph it. That's weird. Usually the graphing is up here. That's very strange. Oh no, that's because it's already down here. Okay, so you can see there's an asymptote, as we kind of predicted. We said that we cannot have either -2 or +3. And so, though it's very hard to see, this would be 3. Oh, I can't write on it. All right. 3 for this first vertical line and -2 over here. It does say they're trying to help you here. These are, as we know, referred to as asymptotes. And then on top of that, the range, although it doesn't ask for this in the problem, does not include 0. There's no value of x that could cause y to equal 0 here. So we've got 3 asymptotes, 2 vertical ones. So the domain excludes these 2 and negative 3, yes, no, sorry, 3 and negative 2. And then that's what this thing looks like. Okay, so in other words, yes, what you found here is asymptotes. The function cannot have a value at those points because it would lead to division by 0. Man, that's a wild looking function. I don't know if there's a name for this kind of thing. I'm sure there is. I just don't even know what it is. All right, now this one, it's a little bit simpler. There's only, yes, there certainly is a value of x that could cause division by 0. And what would that be? Well, let's find out. So that's the only value of x that could cause a problem. So usually with these cases, what you're looking for is a value of x that either leads to division by 0 or the taking of a negative square root. That's normally what we will encounter. So here the domain is everything from negative infinity up to, but not including negative a half. And then everything from negative a half up to positive infinity, not including a half. All right, let's see what this thing looks like. In Symbolab, which, well, of course, this shows us that there's going to be an asymptote at negative 1/2. All right, let's go back there and try this one on for size. 3x plus 1 is divided by 4x plus 2. I think it really makes a big difference when you can see what these functions actually look like. It's quite a talent to be able to visualize these functions just by looking at these equations. It takes a ton of practice. Look at that one. So you can see right across here, this would be, oh, it's got 2 asymptotes. The one that we're looking for, though, because we're looking for the domain, we're looking for the vertical asymptote. Oh, delta math. Yeah, you know what? I keep writing notes to myself to look into it, and I just haven't gotten around to it. I will, don't worry. But I just, it's just the first couple of weeks of the semester are always crazy busy. And so far, don't worry, we'll be losing it because it's a great way to get more practice. So that's what I'm definitely looking into that. But like I said, it's just been like the first few weeks of any semester are always insanely busy. So don't worry, I will get to it. All right, well, anyway, so we're looking for a vertical asymptote, which happens to be, and again, it's very difficult, although here's the negative 1, here's the 0, it's negative a half. Yeah, I wish that graph paper was a little bit more noticeable, you know what I mean, the grids. And if you do it on here, it's just so big, it's hard to see anything. That's my opinion. I don't know why they do it that way. But anyway, yes, but it does prove what we were saying, that there is an asymptote at negative a half because that's where the function would have a discontinuity since we cannot divide by 0. Now, this one is as straightforward as it gets, although maybe not. At first glance, it looks like it's going to be easy, but then we notice something else here. Certainly, x can't be 4. But what else can it be? It can't be less than negative 4 either, because if it is, we'll get a negative square root. So therefore, it can be negative 4. That will give us division by, 0. So we can start with negative 4, but we can have negative 4. So we'll use the square brackets. And then we're fine up until we get to 4, which we're not allowed to have. So this is an interesting case because this is everything from -4 to 4, including -4, but not +4. And this is 4 to infinity. Not including the 4. Oh, I can't wait to see what this thing looks like. Oh, it's going to be a mess. All right. Square root of x plus 4 over x minus 4. It's thinking about that one. And by the way, did you notice that it also, I forgot to show this to you before. This interval notation that I just showed you, it's doing it for you. Look at that. It's right there. This is exactly what we just got through doing. So if you're not sure, you can come here and double check it. Wow, how do you like that? And up here, what they're doing is they're using a slightly different approach. They're saying we've got everything from -4 up to x up to 4, not including 4, because this is a strict inequality, and then strictly greater than 4. All right, and the graph, woohoo, that's a weird graph. So as we said, it starts at -4. There's no values of x before that. And then after that, the only value that's disallowed is 4 itself, which means we have an asymptote there. How do you like that? It just sort of stops right there. Interesting. Well, then what about this disaster? You got 2 square roots. So that means there's 2 things that can cause a blow up, 2 or 3 things. Let's see, what can't we do here? Well, in the first one, x can't be less than 6, because that would cause division, a negative square root. And the denominator, x can't be less than 4. So that actually includes the one on top. If we can't be less than 4, we also can't be less than 6. So really, there's only one constraint, and that's it. So it'll be 4, infinity. And that's it. Oh, wait a minute. What am I saying? No, wait, no. Yeah, no, that's right. Because if you put a 4, oh crap, I just realized, no, it has to be 6. My fault, sorry. It's the other way around. Yeah, that's right. It has to start at 6, because then at 6, this one is 0 and this one is positive. If I allow a 4, yeah, then that's going to be a problem down here. So this is 6. Yes. Very good. Yeah, I almost blew it. That's good. Oh, yes, but it does allow for a 6. So we'll put the square brackets, because 6 would make this one 2, and this one would just be 0. Okay. All right. And again, well, just for the fun of it, let's go see what it looks like. In the numerator, we have the square root of x minus 6. And down here, square root of x minus 4. Let's see what it looks like. I'm sure it's going to be very bizarre. But first, let's confirm, yes, they agree with us. The domain is 6, everything from 6 up to infinity, including 6. And this is what it looks like. Whoa. Yes, that's very peculiar. But okay, that's it. It's just 6 and up, and that's all we have. But you notice that in the range, we have an asymptote of 1. There's no value. I'm not sure how you would prove that without a lot of messy algebra, that the y value can't exceed 1 or can't actually even equal 1. Luckily, we were not asked to do that. Sometimes the range can be a nightmare to figure out. But all right, anyway. So now, average rate of change. This is a completely different type of situation. The formula that we need here is this. Let me type it in for you. This is more of an applied thing. You notice with the pre-calculus, some of these concepts are very theoretical, and some of them are meant to be very, very practical. Ultimately, Newton invented calculus to help him explain the laws of physics that he was creating. It was like, well, there's not enough math. There's no math out there that can explain what I'm doing. Therefore, I will invent it myself. And so it was intended to be very practical. So that's when you know your stuff, when you have to invent an entire new branch of math just to explain your ideas. That's pretty impressive. But that's because he's Newton. So we'll have f of x2 minus f of x1 all over x2 minus x1. And this is just the slope of this function between those 2 points. That's really all that it is. It says the rate of change, but that actually means the slope. Okay, now the 2's are coming from here. So in other words, because of the way this interval is written, x1 is the 1 and x2 is the 5. Which means we have to figure out f of x1 and f of x2 ourselves from this function. Okay, so f of 1 is 1 squared, which is 1. This is what we mean by f of x1. Actually, let me write it like this. I think it's a little bit cleaner this way. F of x1 is f of 1, which is equal to 1 squared, which in turn is equal to 1, of course. F of x2 is f of 5, which would then be simply 5 squared, which is 25. And now we have all 4 numbers, and we can go ahead and plug them into this equation. So we're going to have oops, 25 minus 1 in the numerator divided by 5 minus 1 in the denominator. So we're going to have the ratio of 24 over 4, which is 6. That's it. So the average rate of change over that interval is 6 with this function, that is. So let's see if we can visualize this. All right, well, it's not drawn as well as it could be, but Okay. And so basically, if you have to imagine that there's like a tangent line here somewhere, I'm not doing it very well. All right, well, that's supposed to just touch the curve at one point, but the slope of this thing, yeah, it's not the best, but you get the idea. It's a straight line, it's a tangent. The slope of this line touches the curve at one point. The slope is 6. Okay. So yeah, it's very difficult to draw right here, but that's what we're trying to accomplish here. All right, now down here, so I'll just copy this formula again. And we'll do this all over again. Now, x1 is the -4. Okay. So x1 is the first number in the brackets. -4 rather. And x2 is the 2 right here. So we have to figure out for ourselves f of x1. That would be -4 cubed, which is -64. F of x2. Actually, let me do this one more intermediate step. There we go. And then f of x2 is f of positive 2, which is 2 cubed, which is 8. So now we just apply these numbers to the formula. So we have 8 minus a -64 over 2 minus -4, 72 over 6. And 72 over 6, is that right? Did I do it right? Yeah, that's right. Yeah, no, we're good. Okay. All right, so that's 12. Now the next one is, it's getting a little trickier. F of, so x1 is -2. That's the value on the left of that interval. X2 is 4. F of x1 is 5 minus 2 times -2 squared, which is 5 minus 2 times 4, which is 5 minus 8, which is -3. And then f of x2, is 5 minus 2 times 4 squared, which is 5 minus 2 times 16, which is 5 minus 32, which is -27. All right. Now we're ready to plug this in. All right, f of x2 is -27. minus a minus 3. And then we have 4 minus a minus 2. So we've got, so this numerator is actually negative 27 plus 3. Down here we have 6. So we end up finally with negative 4. All right, and there's one more here. Let's move this down a little, and we'll get the equation right here. All right, so this time x1 is negative 3, and x2 is positive 3. F of x1 is 3 times negative 3 cubed minus 1, which is 3, negative 3 cubed, minus 27, minus 81 minus 1 is minus 82. F of x2, on the other hand, would be 3 times 3 cubed, which is positive 81 minus 1, which is 80. All right, now we're ready. So we have 80 minus minus 82. And then we have 3 minus minus 3, which is 162 over 6. Which is 27. It's hard to believe, but that's 27. That's right, 140, yep. All right. Okay. All right, so those are done. I think we're now pretty good at this. And now we're going to try something different. We're going to look at functions again. So far, everyone's doing okay with this, I hope. Good. All right. So f plus g simply means, it's just a shorthand way of saying f of x plus g of x. Oh, too fast. All right. Let me know. If it's too fast, you just have to stop me. But okay, I'll slow it down. But yes, all of this stuff will be on Moodle when we're done. If you miss something, I guess that means my typing with the equation editor is pretty good. If I'm going too fast, I was hoping that would sort of slow the whole thing down, but apparently not enough. But all right, well I'll remember that. Thank you. All right, so f plus g would mean just literally add these two together. In fact, I'm going to copy and paste these. This is one thing I can't do on a whiteboard, which is kind of nice. Also, we can't record what's going on the whiteboard. So literally all you're doing is adding these together. And then, usually the convention here is to try to combine these in such a way that the first, eliminate anything that you can, but also write them in descending order by exponent, Okay, like here, for example, this one is different because the x squares drop out. And so you very simply end up with 2x plus 6. But if we had an x squared term, we want that to come first. You always want the highest exponents to come first in these cases. It's just a convention. It doesn't really matter. But this is what mathematicians like. So we want to do what they like. All right, now here you're just doing the opposite. You're subtracting them. Okay, instead of adding, we subtract. So we're going to end up with these first two terms haven't changed. Then don't forget to apply the negative to both the 6 and the x squared. And you know, the thing is, one of the easiest ways to make a mistake in math, no matter what level you're at, is to mess up the negatives. It's just too easy. Anyone, even Einstein, could have made sign mistakes. I mean, really, it's just too easy. Now here, though, we have 2x squares. And whoops, we don't want that. We also have a 2x, and we have negative 6. All right. Now, the next one's going to be more challenging because we're multiplying. Yeah. Oh, no. But then don't worry. We can use FOIL in this case. And we're going to because it's a very straightforward process. Okay, so let's do the FOIL. And that should take care of it. So, oh, no, let's not use that color. It's nice for pictures, but for actually writing, I think black is always the way to go. It's just easiest to see it. Even though purple is a cool color. All right. Let's see. Let's make some room. F 6x squared. O is negative x to the fourth. Inner is these two, 12x. Outer, last rather, is these two, minus 2x cubed. That's right, isn't it? 6x squared minus x to the fourth, 12x. Yes, okay, so none of these can be combined. So your final answer, and again, try to always write the highest powers first, minus x to the fourth minus 2x cubed plus 6x squared. And then finally we end up with plus 12x. All right. Man, that was tough. Now, the last one is a division. Now, what's great about division is that often we can't simplify it any further. We're done. And this is one of those cases because you're going to wind up with, let me write it in the equation editor. The function, the original, what is it, x squared plus 2x. And in the denominator, we have 6 minus x squared. And guess what? That's it. We're done. It might be disappointing, but we can't consult. Whoops, let's move it down here. We can't do anything else with it. There's no method that we can use to simplify it. So we're just going to, oh man, where did it go? Okay, well, just leave it alone. There it is. That's the final result, okay? Yeah, I'd like to keep them all together if I can. All right. Now, those were just algebraic operations on functions. What's coming next is the composite functions. Those are pretty tricky. They can be very tricky because you're essentially forming one function out of another one. Man, this is good, but very complicated. All right, are we ready to go on to the next batch of questions? All right. So for example, oh my God, look at all of them. So f of g of x means you take your f of x and you replace all the x's with g of x, just like as if g of x were a number. 2 g of x squared plus 1. Now, it turns out that g of x is 3x minus 5 squared. And if you want to apply a FOIL to that, you can. You can write it out like this because that's what it actually stands for. And we'll try FOIL. F O I last. So we wind up with, in parentheses, all of this can simplify. Let me just write it down here somewhere. This actually simplifies to 9x squared minus 30x plus 25. So therefore, I'm going to put that here in the parentheses. And then I'll just multiply it through by the 2 through all of these terms. And then I just have to consolidate the 2 constants. And that's it. Okay, now we're going to do g of f of x. We're going to take this in the opposite direction. So let's just quickly remind ourselves what functions we were dealing with. I'll just copy these down here. So that means g of f of x means just take g of x and all the x's become f of x's. So you'll have 3 f of x minus 5. Okay, and so now we know that f of x is 2x squared plus 1. So this one isn't too bad. There's not a lot of, let's just say we don't have to square anything, that's for sure. So again, g of f of x means take g of x and replace all the x's with f of x. You plug it in, and then you do some algebra. And in this case, that's all you have to do. All right. All right, now the third one, the next one is f of g of 2. All right, so that's an interesting case because now we're going to wind up with a constant. All right, so again, let me just go grab these. So what you need to do here is evaluate g of x when x equals 2. So in other words, g of 2 would mean 3 times 2 minus 5, 6 minus 5, which is 1. So that being the case, f of g of 2 is the same thing as f of 1. And of course, that means since f of x is 2x squared plus 1, whoops, what am I doing with that 5 there? It's 2x squared plus 1, not 5. 2 plus 1 equals 3. That's all you had to do. Now, what you could have done instead, since we've already calculated f of x, g of x, you could have actually taken this. Let's see. Oh, okay. Let me do this. I'm just going to copy it down here and show you that you would have wound up with the same result. Suppose instead you had already figured out, which we did, that f of g of x is 18x squared minus 60x plus 51. And then you just replace the x with 2. Okay. Oh, sorry, I wrote it incorrectly. I just realized it. It's minus 60x plus 51. And so you end up with 18 times 4 minus 120 plus 51. So this is 72. And that turns out to be, let's get out the calculators. 72 minus 120 plus 51 is 3. Which is exactly what we got up here when we directly substituted g of 2 into the equation. All right, so let me bring these all together. So in other words, now you can see side by side 2 alternative ways of doing this. But I think you'll agree the first way is the easier way, because then what you're essentially just doing is moving a constant into f of x, and you're all set. In the second case, you had to figure out f of g of x first before you did anything else. So the second approach, I think you'll agree, is a lot more work than the first one. Of course, they'll give us the same results, but let's face it, we want to avoid work whenever possible. That's right. We can admit it. Because let's face it. I mean, you've only got so much time, and when you can save a few steps, you want to go for it because, why would you spend extra time on a problem like this? That's not necessary. Now, for D, we're doing the opposite. It's g of f of 2. All right, so let's do this in 2 different ways again. Now, like I said before, here's what you can do. F of 2 is very simply, whoops, what did I do? F of 2 is 2 times 2 squared plus 1, which is 2 times 4, plus 1, which is 8 plus 1, or 9. So that means g of f of 2 is really the same thing as g of 9. Ooh, now that's nice and easy. So therefore, g of 9, because g of x is only 3x plus minus 5, that'll give us 27 minus 5, which is 22. And now, of course, the other option we had was to go back and grab our definition of g of f of x, which we did all the work. There it is. Since g of f of x equals this expression, it must be the case that g of f of 2 would simply be 6 times 2 squared minus 2, which is 6 times 4 minus 2, which is 24 minus 2, which is, of course, 22. Oh, wait, let me fix that. All right, and again, you've got two different approaches, but I think you'll agree the first one was simpler. Because this one requires us to do g of x, f of x, and then make the substitutions. Okay. Now, then we get into the really oddball ones. F of x. That's what this actually stands for. You see that FOF. This is just shorthand notation for f of x. Now, that's a strange idea. But we can do this. So remember what f of x means. 2x squared plus 1 So basically, all the x's are replaced with f of x. So f of x means 2 f of x squared plus 1, which means 2 times 2x squared plus 1 squared plus 1. So now it looks like it's time for some FOIL. 2x squared plus 1 What the hell is going on here? My tablet is misbehaving here. Hold on a second. Yes, it is. Technology loves to mess with you what is this? Yeah, all of a sudden my tablet has decided it's tired. All right, so I'll have to smack it around a little. No, it's doing the same damn thing. I have no idea what's causing this. Well, that was just weird. All right, so let's try that again. That's what this actually means. And so we'll apply FOIL to it. F O I L. There's F. 4x to the fourth. Be careful with that one. This is 4. We're multiplying these two 2's together to get the 4. And then we have x to the 2 plus 2 power because they're both the same base. Just a little quick reminder there. When you multiply 2x squared by itself, you end up with 4x to the 4th. That's F, and O would be these. 2x squared. I is the same thing. And here's last, which is just simply 1. So we end up with 4x to the 4th, 4x squared plus 1. And that belongs inside these parentheses. All right, so let's make that substitution. Let's do that right here. So this is the equivalent of 2 times 4x to the 4th plus 4x squared plus 1, and then we have plus 1 at the end. Okay, so in other words, 2 times, this is all this expression over here squared plus 1. Now we have to multiply everything here by 2. 8x to the 4th plus 8x squared, squared, plus 2 plus 1. And so when we're finally done, we get 8x to the 4th plus 8x squared plus 3. And wow, that was tough. I think the next one will be a little simpler because g of x was a little bit simpler. So that's it. We're done. All right, there's one more way down here somewhere. There it is. It got buried after all that. G of GOG there, like that, simply stands for G of X. All right, let's make that a little bigger. Now, the original function G of X was from way back, here it is. This one shouldn't be too complicated. All right, so that means that G of X equals 3G of X minus 5 equals 3x minus 5 minus 5, right? So you can see it's the X was replaced with G of X equals 9x minus 15 minus 5. Wow, that was easy. 9x minus 20, and then we're done. Wow. That's it. Oh my God. Both problem sets are done. Woohoo. Wow. All right. So that's the first two problem sets. There's the third one we can save for next week because we haven't gotten to that material yet. So here's what I want to do. Now, normally we have a break right around this time anyway. This is good timing. When we get back, I want to show you some fun videos, which one of which I already mentioned last time. And they're interesting. They're a lot of fun. You know, math has a fun side to it, as you know. And so these are very thought provoking, but they're also kind of fun. I think we deserve some fun after all of this. And then we can go back and dive back into part one, chapter 1B. And if we finish that, we can maybe take a peek at chapter 2. We'll see how that goes. We'll play that by ear a little bit. All right, so let's knock it off for a bit. And when we get back, have something fun to look forward to, those cool videos, which will make you think very hard about what math is really all about. Okay, so all right, I'll see you all in a few minutes. All right. So now, like I said, we've got some interesting videos to watch. Just they won't take too long. They're fun and they're definitely worth watching. So what I'm going to do here is I'm going to put the link into the chat box. Now, I've discovered from experience that if I try to show it on my screen, the chances are pretty good that for whatever reason, the sound may not come through and you may not be able to hear it. So what I typically do with these classes is I just have everybody watch it on their own computer. So in order to do that, I'll be posting the link into the chat room. And then in order to avoid any issues with YouTube, I also will be pausing the recording so that if you watch this recording later on, the video won't be part of it, but you will have the links and you can watch it again anytime you want to. All right, so we're going to start. Let's see, we're going to start with, our prime numbers made up. Boy, that sounds like a challenging topic. Our prime numbers made up. There we go. So we're going to look at this. So let me put this in the chat room and you can see the link right here. And so just click it on and it should start working right away. All right, when we're done, we'll come back and we'll go over it a little. And so hang on, there it is. So let's take a look. All right, is everyone done? Okay, I'll give you a couple of minutes. But that one was pretty intense. The next two are not quite that deep. They're getting very philosophical on us there, which it's interesting. But I like that Goldbach conjecture. It's kind of interesting, the idea that, as they said, if you take any even number, anti-realism. um, yeah, this is what I mean. They're getting a little more into philosophy there than math, but I guess when you're looking at the big picture, it can't really be helped. But yeah, the Goldbach conjecture, which just says that any even number greater than two can be expressed as a sum of two prime numbers, which you don't notice these things unless somebody points it out to you. The problem there is that they still don't have a formal proof for this. And in math, that's a big deal, because all the results that we know at some point have a formal proof, which just shows that it's always true, no matter what numbers we choose to use. Here, instead, what's happened is they've used computers to test all these even numbers and in each case, they've been able to find. I know. How would you prove that? I don't even want to think about it. It must be unbelievably complicated if nobody's come up with a proof in all these centuries. Um, but what they did instead was they got into the computers and they just tried all the different even numbers. And they were thinking that, if we could find one counterexample where it doesn't work, well, then we can show that the Goldbach conjecture doesn't always work. But they did not find one. So in other words, they've been pushing it to the limits, and they still haven't found a counterexample. But there's also no proof. So that means we can't really say for sure that it always works until we have that proof. We can demonstrate it with a computer, but right now that's the best we can do. In fact, that's why it's called a conjecture, because it means that it still hasn't been formally proved. Once they do prove it, then it can become a theorem. Okay, then it gets promoted to theorem, which means that it can be proven to always be true. Poor Goldbach. Now, the other mysterious problems in math have been solved in recent years. There are a few proofs kicking around from the 17th and 18th century that nobody could figure out. And what ends up happening is that mathematicians are sometimes able to use computers to help them generate these tremendously complicated proofs where that wasn't really possible in previous centuries. So I guess if you want to become a theoretical mathematician, this could be your life's work, trying to prove the Goldbach conjecture. But anyway, let's look at the next two videos are also kind of conceptual, but I think they're not quite so philosophical. So let's take a look at this next one called Interesting Facts About Numbers and Prime Numbers. This is meant to be more about how they overlap with the real world. So let's take a look at that. I think you'll find this very interesting. All right, so I'll pop this into the chat room again. And all right, let's take it away. Numbers have also held different meanings throughout cultures, although we deal with them every day. Much to surprise, but
step of Aristophanes was the earliest method of finding prime numbers.
All right, are we done? Okay, good. Now that was there was actually it was great. There was just a little too much information going on. It's you start to forget after a while all the cool things that they mentioned. But the one thing that caught my eye was like the guy was reciting the numbers. Did you? I don't know if this was true or not, but they showed him having an actual audience of people watching him. Can you imagine anything? Oh, the Rubik's Cube is unbelievable. But I mean, can you imagine watching somebody recite the numbers? How boring would that be? Yes, the Rubik's Cube, it's insane how many different combinations are. You can find these people who can do it in like seconds. I don't know how they do that either. But the funny thing is that Rubik's Cube, the inventor, I think he was a mathematician. He was, I don't remember but he came up with this idea and he made tons and tons of money in the 80s from it. And I guess they still make them. But for a while, it was really a big craze. Everyone wanted to do the Rubik's Cube. But oh my God, it's just unbelievable. And so, yes, that's a lot. That's why if you don't know what you're doing, it's going to take a long time to finish it. But all right. Anyway, so there's just one more. This one, it's a little bit more conceptual, but it's a fun conceptual video and it involves infinity because what it's trying to get across is the idea that there are different levels of infinity. It isn't just a single concept. There actually are different kinds of infinities, which we'll be looking at next. And then when that's done, then we can get back to work. Okay. All right, so this is the third and final video for the day. Let's take a look. And it's called the Infinite Hotel Paradox. Yay. All right, so it's going to be conceptual but fun at the same time. All right, let's see what happened. Where's my chat room? Oh, that's interesting. Oh, I'm staring right at it. No wonder. All right, here we go. This is it. Mm. Yes. um, yeah, they're just showing you how we can prove that there are larger levels of infinity, and it's very interesting. It's very concept, but yes, PTSD. You might get that from thinking about all this stuff. Um, but it was fun, wasn't it? Yes. So, you know what I noticed here? I actually have this other video, which I showed another class of mine, which explains in very great detail why you can't divide by zero. You know what? I think we can spare a few minutes. I'm going to bring it out now and show it to you. Um, oh, the name of n plus 1, really? Oh, I'm not sure what that is. But anyway, completely forgot about it until just now. The reason why I want to mention it, we didn't. This is our first time watching videos, isn't it? Have we seen this video? I'm under the impression that we haven't had any videos yet. Oh no, we've already seen it. Oh, sorry, my fault. Yes, we have. All right, never mind. I guess we have to get back to work. So, all right, let's carry on. Oh, that was a pretty cool video. I think you'll agree. Division, why we can't divide by zero. Don't worry, there's plenty more coming. I've got lots of cool ones coming your way, but we have to wait till we've covered these topics before we can actually see the videos. So in the meantime, let's get back to chapter 1B this time, where if you look at the slides, they're broken up into 1A and 1B, mainly because they're just so long. So 1B starts off, this first part is really just a discussion about graphs, which is okay, it's interesting, but then we'll dive more deeply into some other key topics. And what's good about this is we can now confirm all of these with our friend Symbol Lab. Let me get it down here so we can double check all of these results. Let's see what happened to it. It's here somewhere. All right, I'll just open it back up again. The one thing I don't know if Symbol Lab can do is show two graphs at once, two functions. I have to investigate that. In fact, I bet somebody's already asked that question before. It might be fun to be able to see everything side by side. Maybe not. What do you mean? What happened to Symbol Lab? Oh. Maybe not. All right. It's not perfect. We'll live with it. All right. So anyway, what we're going to look at here is different ways in which functions can be transformed, and what we're going to see is the corresponding impact on the graph. All right. So there are ways in which we can shift a graph to the left or the right, or up or down, or some combination of both. Now, there's a lot of very technical names here, like reflections and stretches and compressions and all this and that. And we'll get through them all, but don't worry, it's not as scary as it looks. Okay, so we're going to consider a vertical shift, which means up and down, horizontal, left and right, some combination of both. Reflections, we'll see what that means when we get to that point. Stretches, same thing. And compressions are just the opposite of stretches. So, all right, don't worry, we'll see them all as we go along. Okay, so why don't we start with the vertical shift, and let's see how this works. All right, you don't have to write all these down. We'll get to them one at a time. So the vertical shift means that it either goes up or down. And so what that means is you're taking an existing function and adding a constant to it. If that constant is positive, the function will shift up. If the constant is negative, of course, the function will shift down. It's just that simple. Now, I've got a bunch of graphs here from Excel, that will try to illustrate this, but I've mentioned this before. Excel is just okay for these kinds of graphs. We might have to turn our attention to Symbolab if we're not getting anywhere with this stuff. All right, so let's look at a simple example of this. How about this one? This is a cubic function, and the one directly below it is the same function with 10 added to it. All right. So I've already drawn this for you. And in Excel, you can see that f of x, the original function, is the blue one, and orange is the new function. And you can see that they're perfectly parallel to each other because the only difference between them is a positive constant. If I'd added a negative constant, then orange would be directly below blue, but they would have the exact same shape. Dilations. Ooh, I don't think that's in the book. Let me just double check that real fast. Yeah, I don't, let's see. Yeah, I don't believe this book mentions that. So I think we'll just skip over it for now. But I mean, I don't know, maybe later on we'll come back to this. Yeah, the book didn't seem to think it was that important. So I guess we're not going to see that one here. But anyway, so here's the shift. And the shift is as easy as it gets. Add or subtract a constant, and you've got your shift. Now, left and right, this is a little bit more challenging because now we're moving along the x-axis rather than the y-axis. So how does this work? Suppose you have a function f of x, and then you create a new function, g of x, which is f of. Now you notice we're not adding or subtracting a constant to the whole function. For each x, we're either adding or subtracting this constant h. And I think they chose h to remind you that this is horizontal. And surprisingly enough, if that h is positive, the entire curve will actually shift to the right. And if it's negative, the entire curve will shift to the left. Okay, so let's see some examples of this. So again, the key to the whole thing now is that this h isn't added on at the end, like with a vertical shift. This is now replacing x. All right, so let's see how this works. So I've got f of x is this function x minus 3. If I replace all the x's with x minus 2, then this turns into x minus 5. And then we're going to see, now both of these are straight lines, by the way, that x minus 3 is, well, we'll see when we get to it. Okay, so they're parallel. They're not, well, they're actually parallel because the slopes are both 1, but what's different is the vertical intercept. All right, so are we ready? Let's take a peek at this. So the original function is f of x, and the intercept is -3. The new function has an intercept of -5. So you can make the case, well, yeah, I mean, it's hard to, you can see why you might try to claim that this is a vertical. I'm not so sure how you would make that distinction, but you can make the case here that the orange curve is shifted to the right of the blue curve. Although let's face it, in this case, you can easily see it's just this one case though, where it also is shifting up or to the right. But in general, like if we picked another function, as we'll see in the next graph, it'll be more clear that we've definitely shifted it either to the right or to the left. This is just one of those, because it's a straight line, you could think of it as being either down or to the right, because it means the same thing. since both of them go on to positive and negative infinity. But if we have a quadratic function, that's a different matter altogether. All right, so we're going to see that in a minute. If instead of f of x being a straight line, we have a parabola. So I'm going to replace this with f of x plus 1. And you can see I replace this x with x plus 1. And the result is that I end up with x squared plus 2x plus 6. Now, here are the key details that h is minus 1, which is negative. And we saw before that this implies that the function will shift to the right. It sounds backwards, doesn't it? But that's exactly what we're going to see. We've got two parabolas, and one of them will be a rightward shift of the other one. All right, here we go. You ready for that graph? Yes, you are. Let's see. Yeah, see again, I mean, it's kind of hard to tell. I don't know. I think this is a poor example because you can see it's sort of, it's kind of strange. It seems to have gone to the left. I don't know how they can consider this a rightward shift unless I didn't draw it properly. Oh, I know what the problem is. You know what it is? By subtracting 1, remember it's x, I know why this is off. Yeah, this is my fault. You know why? Because h is actually, no, h is negative 1. What am I saying here? This is g of x is actually f of x plus 1. If you write this as f of x minus h, that implies, no, h is negative 1. Wow, I don't know. I'm not so sure about this one. They claim that if h is negative, then we're shifting to the right, but I don't see that here. Okay, something's not right. Oh no, I just had it backward. It does say that. Oh, all right. No. I'm not imagining things. It was right the first time. Positive does mean to the right, and negative means to the left. All right. Okay, so the notes are fine. Don't worry. I just screwed it up myself right now. I just misremembered that this actually means left. Sorry about that. Okay. I guess it's too early. It's not that early. It's too early for hardcore math thinking. No, it's not. I just goofed it up. So yes, I'm sorry about that. Negative does mean to the left. It did say that. I don't know why I got it backwards. Okay, so h is definitely negative 1 because we're subtracting negative 1 to come up with x plus 1. So all is well with this stuff then. We are shifting to the left, and you can see it a little more clearly here. You're just essentially just pushing it over this direction. So that one worked. And then sometimes both of them can change. What does that mean? We can shift both of them by doing two things at once. So this is our starting point. And what we're going to do is basically turn it into f of x minus h plus some constant. So we're getting two things at once. This is our horizontal shift. And this is our vertical shift. And so both things are happening at once, and therefore we'll expect to see both in the graph. All right, so here's an example. Now here's our f of x. How are we going to convert this into g of x? The h that we've chosen, let's see, it looks like it's 3. So remember, g of x is f of x minus h. So therefore, h is positive 3, greater than 0, and that shifts to the right. And then on top of that, there's an extra 20 here. We've added a constant, which is greater than 0. So this is a shift up. Okay, so when the constant is positive, we shift up. And when we subtract a positive number, the shift is also to the right. So the new function, we started out with f of x is x squared plus 5x minus 1. And now g of x is this. Now, it would be hard to tell just by looking at these what the relationship is between them. But we know that h is positive, and this constant is also positive, which means whatever this one looks like, g of x must be above and to the right of it. It's like it's moving in a northeasterly direction. So let's see what that actually looks like. Let's confirm this. All right, and again, oh no, you can kind of see it. It's moving up and to the right. All right, so that's that. So far, Excel is holding up very well, I must say. So orange again is g of x. This blue is the original f of x, and you can see how they look compared to each other. Oh, yes, go ahead.
I apologize, Professor. I was wondering if you could maybe explain what causes this again. It was a bit confusing.
Well, yeah, so the constant just is a straight up or down shift. What's happening here is that we are subtracting 3 from x. So in other words, let's go back here. So you can see g of x, instead of having plus 5x, it is minus 1x. So you can see what's actually happening here is, in a way, the curve is getting more, let's say, flattened out, I suppose you could call it. And so it doesn't rise as quickly as f of x now does. And so that's why you have this right shifting appearance. What's really happening is, you can think of as flattening it. You see how it's not as steep? And that's because what's happened is, with the x, we have negative x instead of, so this is negative 1 instead of 5. So that flattens out the function. And then we also, on the other hand, have a larger constant. That's what's responsible for the upward shift. All right, so does that make sense?
So basically, having both a negative and positive constant makes it go up and towards
Yes,
the right.
the constant means up and down. The subtraction, this part, is what determines left and right. Okay, so again, the way they've written it, if h is positive, so in other words, you're subtracting a positive number, this shifts to the right. And if h is negative, which means this is x plus something, that moves it to the left because it gets steeper. So it's sort of like, I'm trying to visualize what this would be like from here, let's say maybe to here, this kind of thing. And we can try more on so the only problem with the Symbolab is I don't think it can do 2 graphs at once, which would have been nice. Anyway, so reflections are different because with a reflection, there's 2 ways we can have a reflection. with respect to the vertical axis or the horizontal axis. Like this is a reflection. With respect to the horizontal axis. On the vertical side, I don't know of any. Well, let's just say that if you had something like this going on, which I don't know the graph of this, or the function, but this would be what we would call a horizontal reflection. And this would be a vertical reflection. This one on the left is like looking in, let's say, a lake, a very still lake, and you see yourself in the water. The one up here is more like a mirror, okay, over here, because you're looking in the mirror and you're basically seeing, you know, the reverse of yourself. You all know that, right? I mean, when you look in the mirror, you're not seeing what everybody else is seeing because your image is being reversed. Okay, it's kind of weird, but that's how it works. So let's start with the horizontal ones, left to right. So here it's so easy. All you have to do is replace x with negative x, and that will take care of it. So for this function, so g of x would be f of negative x, which means negative x squared plus 5 times negative x minus 2, which is x squared minus 5x minus 2. So it's the same except for the sign of x, the sign of x. The 5 is the same, but the sign is different. And so let's take a peek at this. Oh, see now, yeah, they're kind of, yeah. Let's see, how would we describe this best? If we basically have to imagine there's a line here, vertical line, and see they're staring across at each other like this. So it's like this is essentially our mirror right here where they cross. And except for the colors, what's going on the right-hand side is a match for what's going on the left-hand side. So ignore the colors and you can see the right-hand side and the left-hand side are identical to each other. And assuming this is our mirror. Okay, that's what we mean by horizontal reflection. Now, a lot of this discussion is motivated. Keep in mind that throughout history, up until maybe, 30 years ago, if you wanted to look at a graph of a function, you had to draw it yourself. You had to understand what it was all about. It's only, since people got their own computers at home that it's become possible to have software that does this for us. But so a lot of these techniques were designed by people who did not have access to computers to help us visualize what these functions look like. It's like before they had calculators, how did you come up with a square root? There's actually a technique you may have been taught in high school where you can actually take roots, square roots, with a method invented by Newton, but it's pretty complicated. And but it works. It works very well, as a matter of fact. But once calculators became available, that was that. Nobody learns how to do that technique any longer. So here, some of that is going on as well. The idea here is to really understand how these functions are related to each other. But, I think ultimately the best way to understand this is to look at the graphs, which fortunately Excel can do for us. Now, vertical is up and down. Okay, in here, you're replacing f of x. Whatever f of x is, g of x is not f of negative x, but instead it's simply negative f of x. So if we started here, g of x would therefore be negative the whole thing which means negative x squared minus 5x plus 2. It's just all being reversed. And so even though, I mean, when you see the graph, you'll say, oh, yeah, I see what you mean. It's now, you've basically flipped it upside down. That's essentially what you've done. Let's prove it. Okay, see now they do overlap, but yet you can see very clearly that if you think of the horizontal axis as the surface of a very still lake, when the blue curve looks in the water, it's not a perfect analogy, but you can see that they're the same from top to bottom. What's going on above this line matches what's going on below the line, except for the colors, of course. Now, they don't have to overlap like this. That just depends on what particular functions you've got. You could have something like this too. It just so happens that these do overlap. Okay, but it doesn't always work that way. All right, what else did we have here? Oh, odd and even functions. Now, this is an interesting idea. By the way, we're done now with that graphic stuff. The graphs are fun, but it's time to get back into the other material. A function is said to be even if for every x, f of x equals f of negative x. On the other hand, a function is said to be odd if for every x, f of x equals negative f of negative x. Now, it turns out that many functions do not fall into either of these categories. So it's not the case that everyone is one or the other. It's not like the natural numbers where they're all either even or odd. Here, if this happens to be the case, then we say that it's an even function. And here it would be considered an odd function. And it should show up in the graph. But all right, let's take a look. How about this one? Now, remember what we're trying to prove is, let's see, now how would you prove this one? F of x equals f of negative x for every value of x. So what you would actually do is this. F of x is x cubed plus 2x. F of negative x means you replace all these x's with negative x. So what is our conclusion here? Not even. Because these are not the same thing, are they? No. But it might be odd. Let's see what that would be. Negative f of negative x would be the negative of what we found here. Because this piece by itself is f of negative x. And so you've got x cubed plus 2x. Oh my God, they're the same. So this tells me that this function is odd, or is an odd function. Now, I don't know if that's a cause for celebration or not, but what we've done is we've been able to demonstrate that it's not even, but that it is in fact odd. Okay. So I don't hear any cheering. No, there's nothing to cheer about. It's just, well, that's just the way it worked. This function is odd, and we can prove it. Now, you notice, just like with the Goldbach conjecture, we didn't say, well, let's try f of 2 and f of negative 3 and see what happens. We were able to demonstrate that no matter what x is, this will always hold. And I guess you could think of it as a kind of, maybe not a proof, but we were able to demonstrate that this is true for all x's. And that's the key to the whole thing. It must always be true. So when you go to the store and you buy something and it's, let's say the price is even, like $18, You might find yourself, without realizing it, subconsciously trying to think of the two prime numbers that add up to that. And you might say 18, what would that be? Oh, 5 plus 13. There it is. It's a fun game. You can play it anytime you want to. Just grab a random even number and try to come up with the combination or the sum of primes that makes up that number. And see if you can come up with a counterexample. You will not. All right. Mathematicians have gotten this up to such high numbers that you'll never find one, but it's interesting to think about it. All right. So this is just what we just did. Let's try another example. Oh, so now this is what it looks like. And what's interesting is that it is symmetrical. Ooh. So I guess the way to describe this, in effect, they're kind of mirror images, aren't they? Don't you think, from quadrant 1 to 3? Yeah, it's kind of an interesting function. Yes, go ahead.
So since odd functions and even functions seem to be inverses of one another, does that mean the graphs for even functions are going to be asymmetrical?
Let's see. I hope I have an example down here. Here's one. This is an even function. We'll prove it in a bit. And you can see, so I think the logic here is this. The even function is symmetrical about the vertical axis. The left and the right are mirror images of each other. Okay, what's going on over here is exactly the same as what's going on over here. So you have to imagine that the vertical axis is a mirror. Whereas with this one, it's sort of, if let's just, they're not exactly lined up. I think you could make the case, though, that if you were to hold this on top of a lake, that you would see this directly below you in the reflection in the water. So we could say here that the symmetry is with respect to the horizontal axis, although not exactly, because they're not in the same spot here. From here to here, though, you can see that there is symmetry going on. It's just that one is not directly above the other. So it's kind of a symmetry from here to here, basically. I don't know. But anyway, let's just take this function right here and just prove that it is in fact even. It would be x squared minus 7. So remember, this is how we formally define odd and even. Let's try odd. Let's see if this is an odd function. If this is the function, then what would be the value of negative f of negative x would be negative. And now here we replace the x with negative x. So we're going to end up with negative x squared minus 7. Oh, no good. But for even, let's see if it equals f of negative x. You're going to have negative x squared minus 7. Oh, yes, they are the same. So this proves that this function is even, because f of x and f of negative x are the same thing. All right. And then we've already seen from the graph that this implies that it will be symmetrical about the vertical or y-axis. Well, Oh, I see. I thought we were done with the graphs, but we have a couple more. A stretch. Now, we all know what a stretch is. You have to imagine that these functions are made out of some plasticky material where you can grab them and stretch them out or shrink them up. So what we're doing is we're taking our original function, and then g of x is some constant multiplied by that. Now you notice it's not added to it, it's multiplied. And so whether it becomes a stretch or a compression depends on whether a is positive or negative, as you can probably guess. So let's see a couple of cases here. Oh, we're comparing it to 1. Ooh, this is tricky. A has to be greater than 1 to make it a vertical, meaning up and down, of course, stretch. If it's between 0 and 1, there'll be a compression. Ooh, now this one looks intriguing. Negative A means it will either be a stretch or a compression. That will depend on the magnitude of A. And then there could also potentially be a vertical reflection. That's a weird case. Okay, negative A, man. Let's see what that looks like. So we'll start out with a simple case, a simple parabola. All right, and we're going to see what happens. All right. If we start with f of x is x squared plus 2, we simply multiply that by 3. Let's see what happens. So a is greater than 0. Where was that? Oh, this is a typo. It should have said 1 right here. This is a vertical stretch. Okay, so all right, let's take a look at what it looks like. Yeah, you can see it's hard to tell on the right-hand side. It's really kind of weird. I think this is an Excel problem. You'd think they'd be completely on top of each other, but because the orange one is steeper, but I don't know if Excel is doing a particularly good job with this. I don't know. I'm a little concerned about this graph, but anyway, the orange is sort of it's like let's say it's like a flower. It starts out like this and it closes up at night or something like that. This is how I would think of it as a vertical stretch, but sometimes it's hard to tell with some of these Excel graphs. But if we do the opposite, like if a is a fraction, oh, see, that one looks good. Because you see what's happening is that G is being flattened. So I guess the word compression could be thought of as flattening compared to the original function. Whereas this one was supposed to be like steeper, let's say. So I don't know. I think the word stretch is a bit confusing here. The function, you see how it's getting sort of tighter, like this flower. It's starting to close up at night when the sun goes down, as opposed to here where it's the other way around. All right. Now, what about the intermediate case? It's negative. Oh my God, what is that going to do? All right, so we started with x squared plus 2. Now that becomes negative 2x squared minus 4. Oh my God. Yeah, you can see it's not only it's sort of stretched in the sense that it appears to be steeper. If this was sitting on the top, it would look like more like this, let's say. but there's a reflection going on too. So two things are happening. We've got stretching, and we have obviously reflection. This is what I wanted to see earlier, a reflection that is just right on the horizontal axis, but where they do not overlap with each other. So it's not just a pure reflection, because there's also stretching going on. And again, it's very hard to see from this graph. If this one continues, it's pretty flat compared to this one, which is going to continue like this. So it's it's steeper. So I guess we can think of it as. So again, this is with respect to the horizontal axis rather. Now, what about the other cases with horizontal stretches? Oh, now here you notice how this constant is inside. We're replacing f of x with f of b of x. And this one can go either way depending on the value of b. It can be a stretch or a compression. And so let's see how that works. The rule here also is based on 1. Greater than 1, it's a compression. Between 0 and 1, it's a stretch. And if it's negative, just like before, it's a combination of one of those two with a reflection. So this should be interesting. Wow. Look at these complicated rules. But they're not that different than what we had before. The only other thing that's different here is that we can predict in advance how much compression there is when we have compression. All right, let's see how that looks. All right, so here we have the original function. It's clearly a parabola. And now we're going to have f of 2x, which means that b is greater than 1, which means we'll have some compression. F of 2 of x, now remember what we have to do here. Each of these x's is replaced by 2x to get to this point. And when you write those all out, you'll see that the new function is 8x squared plus 2x minus 7. Now, according to the rules that we have before, since b is 2, the compression is with a factor of 1/2. In other words, it should be tighter. Let's look at it. So it is getting steeper. And that's what we're going to call compression, steeper compression. Stretch is flatter, compression is steeper. Okay, that's what it looks like. Kind of cool, huh? It's like a wilting flower. This is a fresh flower, the orange one. This is the one that's been in the vase for like a couple of weeks, and it's flattening out now. All right, let's do another case where b is a fraction. And so we go from here. Now that means, of course, that all these x's are replaced by 0.5x. And you end up with this expression. This is going to be a stretch or a flattening. So again, this is the same starting value, but now we're going to flatten it out. Okay. Yes, so remember before orange was steeper, now orange is flatter. So this one I think is a little bit more intuitively clear what's actually happening. So as long as you can remember, compression means making steeper and stretching means making it flatter. it should be fairly easy to remember what's going on here. All right. Now I think we have one more example, the last case where we have a negative b, where, okay, -2, f of -2x, again, just replace all these x's with -2 down here. And we now have a new polynomial, or in this case, a new parabola, which is 8x squared minus 2x minus 7. So let's see what this thing looks like. Oh. I don't know. I'm finding this one hard to visualize. This graph that I've drawn is not terribly helpful. I mean, it is a compression, which means it's going to be steeper, but I'm not seeing the reflection. It's sort of, I don't know. I think if we drew the whole thing, it might be more obvious. I don't know if I can see the reflection though. But certainly we see the compression because the curve got steeper. Yeah, I guess if we had a wider range of numbers, we could see it better, but I don't know. It's hard to judge. All right, so that's, now I think we got some more graphs here. This one is straightforward. The absolute value, you've all seen this before. It just means ditch the negative. Oh, everything, yeah, this is already on Moodle. You can go get it and look at it right now. Everything through chapter 2 is already on Moodle. The only thing that's missing is the links to those videos. Plus, I'm going to post the solutions after we're done. I always save till after we're done because I want people to really work on the problems. Oh, and Delta Math, don't you worry. I made a big note to myself here. You can't see what I'm doing here, but I've been writing notes down here all along, and that's in the notes. I circled it so that I can't not see it when I look at my notes tomorrow or tonight. All right, so I'm working on that because I know everybody wants more practice. So it's in the works, okay? But I'm glad you reminded me because, you know, let's face it, it's easy to forget stuff, and if people remind you, that makes it harder to overlook them. So, and if I forgot next week, just remind me again, okay? All right, anyway, so let's just quickly look at absolute value functions. I think you've already seen this before. The graph is just like a nice big V. And of course, it's symmetrical about the vertical axis. But what if we change that to, let's say, g of x is x minus 2? So what kind of shift is that? Let's find out. First of all, let's go back and revisit everything we've done so far. So this is basically g of x, in this case, would be f of x minus 2. So remember, that's from way, way back, where when we have f of x minus h, and h in this case is 2, greater than 0. So we would expect a rightward or horizontal shift, meaning the new one will be exactly the exact parallel of this, except shifted to the right by 2 units. And that's exactly what we're going to see. So orange is just 2 to the right. I'll put a +2 here to see that, yes, indeed, it is exactly the same, except that I've shifted it to the right by 2. Remember, when you have f of x minus h. If h is positive, that's a rightward shift. All right, and if we do the opposite, you'll see that it's a leftward shift. Of course it is. So this time, instead of g of x equals x minus 2, we're going to change that to x plus 3, which implies that h is negative 3. And we're going to see in a minute that this gives us a leftward shift. So you'll not be shocked to see what this thing looks like. Why, yes, indeed, it shifted to the left by 3. It's still the same shape. And you notice that it touches the horizontal axis at negative 3. Now we're going to try 2 more. We're going to look at a vertical reflection. Which means we're just multiplying this. This is g of x is negative f of x. And let's see what that turns us into. Ooh, now that's what you call a vertical reflection. Because again, this is a very still lake down here. And what's going on the top is an exact reflection of the bottom. All right, let's look at one more example of this. We're going to do a vertical shift. We're going to have the original absolute value function plus 2. So that, of course, means, remember, that we're just going to have an upward shift. If we change this from f of x equals absolute x to absolute x plus 2, that should indicate that the whole thing will shift out by 2. And that's exactly what happens. All right. Ta-da! Up by 2, and it's exactly the same, perfectly parallel shift of 2. All right, so all these techniques are just designed to help us understand the graphs a little bit better. They're not really a critically important part of this chapter, but it's good to get a feel for how these functions are related to each other, at least graphically. So what we still need to do is solve for some of these different equations. And then in chapter 2, we're going to focus our attention on linear functions, which are very, very useful for practical applications. So here's what we want to do. The third problem set is all about reflections and all the rest of this good stuff. Let's do that next week before we get started. And then what we're going to do is wrap this chapter up, and then we're going to go through our linear functions, which are really, really important in the real world. And then I think in 3, we're going to switch our attention to what are called polynomial and rational functions. So don't worry, we got a lot of fun stuff coming up. But I think that maybe this is enough for one day. We got a lot done. Let's put it that way. And I will be posting the solutions as soon as we're done, or at least this afternoon. And then in the meantime, remember to work on the third problem set from this chapter. And then next week we'll get together again and we'll finish up the problems. We'll carry on with the new material. And I might just have some more fun videos for you. All right. So I'll tell you what, let's stop right here, and then I'll see you all next Wednesday.
Thank you for your time, Professor.
Okay. All right.
Thank you, Professor.
Thank you.
See ya.
Have a good evening.
Bye.